Imagine two black holes, each a gravitational abyss, hurtling toward each other across billions of light-years. In the final moments, their collision isn't just a cataclysmic crash, it's a symphony of energy, releasing more power in seconds than the sun will emit in 10 billion years. But here's the mind-bending twist: the way their merged mass settles into a stable state mirrors the behavior of heat dissipation in a gas, as if spacetime itself is obeying thermodynamic laws. This isn't just a coincidence. Physicists have found that the entropy unleashed during these mergers follows patterns eerily similar to the second law of thermodynamics. How can the universe's most extreme gravity phenomena echo the mundane rules of heat and energy? The answer might rewrite our understanding of both black holes and the fundamental fabric of reality. Physicists have made a surprising discovery linking black hole mergers to thermodynamics, a field that governs the behavior of energy and entropy in the universe. This connection, observed through data from gravitational wave detectors, suggests that the way black holes lose energy during collisions follows patterns eerily similar to the way heat spreads in physical systems. While this might seem abstract, it has profound implications for our understanding of both black holes and the fundamental laws of physics. Let me explain what this means and why it matters. To grasp this discovery, we need to start with thermodynamics, the branch of physics that deals with energy transfer and entropy. The second law of thermodynamics, in particular, states that entropy, the measure of disorder in a system, tends to increase over time in isolated systems. This law underpins everything from the flow of heat to the eventual fate of the universe. Now, black holes, those enigmatic objects with gravity so strong not even light can escape, have long been linked to thermodynamics through their entropy. In the 1970s, physicist Stephen Hawking proposed that black holes emit radiation and lose mass over time, a process now known as Hawking radiation. This implied that black holes have a temperature and, consequently, an entropy proportional to their surface area. But this discovery goes beyond Hawking's work. It connects the entropy of black holes to the energy they release during mergers, a process that has been observed in real time through gravitational waves. Black hole mergers occur when two massive objects, each warped by their own gravity, spiral toward each other and eventually collide. These events are among the most energetic in the universe, releasing vast amounts of energy in the form of gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity. When two black holes merge, they form a single, more massive black hole, and the excess energy is carried away as gravitational waves. For decades, scientists have studied these mergers to learn about the properties of black holes and the nature of spacetime. But the recent findings suggest that the way these mergers dissipate energy is not just a matter of physics, it's a thermodynamic process. The key insight comes from analyzing the energy emitted during mergers. When two black holes collide, the resulting object doesn't just absorb all the energy, some of it is radiated away as gravitational waves. The amount of energy lost depends on the masses and spins of the merging black holes. But the new research reveals that this energy loss follows a pattern that mirrors the behavior of entropy in thermodynamic systems. Specifically, the study found that the entropy of the merged black hole is closely related to the energy carried away by the gravitational waves. This relationship is not just a coincidence, it suggests that the process of black hole mergers is governed by the same principles that dictate how energy spreads in the universe. To understand this better, imagine a thermodynamic system, like a cup of hot coffee left in a room. The heat from the coffee spreads into the surroundings until the coffee cools down, and the entropy of the system increases. Similarly, during a black hole merger, the energy from the collision is distributed as gravitational waves, much like heat dispersing in a thermodynamic process. The study's authors calculated the entropy of the merged black hole and compared it to the energy emitted during the merger. They found that the entropy of the final black hole is not just a function of its mass but also the energy lost in the process. This implies that the merger isn't just a collision of two objects, it's a transformation that adheres to the laws of thermodynamics. This connection is particularly intriguing because it challenges the traditional view of black holes as isolated, self-contained systems. In classical physics, black holes are often treated as objects that absorb matter and energy without interacting with their surroundings. However, this discovery suggests that black holes are deeply entangled with the thermodynamic processes of the universe. The energy lost during a merger isn't just a byproduct, it's an essential part of the system's evolution. This idea aligns with the concept of black hole thermodynamics, which has long been a topic of theoretical interest. But the new findings provide concrete evidence that these thermodynamic principles are not just abstract models, they are real, observable phenomena. The implications of this discovery are far-reaching. For one, it offers a new way to study black holes by analyzing the energy they emit during mergers. By measuring the entropy of the merged black hole and comparing it to the energy carried away by gravitational waves, scientists can gain insights into the dynamics of these collisions. This could help refine our understanding of how black holes grow, how they interact with their environments, and even how they might evolve over cosmic timescales. Additionally, the findings may shed light on the fundamental nature of spacetime and gravity. If black hole mergers follow thermodynamic laws, it could suggest that the universe itself operates under principles that are more interconnected than previously thought. Another fascinating aspect of this discovery is its potential connection to the holographic principle, a theoretical idea that suggests the universe might be a 3D projection of information encoded on a 2D surface. The holographic principle has been linked to black hole thermodynamics, as the entropy of a black hole is proportional to its surface area rather than its volume. The recent findings reinforce this idea by showing that the energy lost during a merger is tied to the entropy of the resulting black hole. This could mean that the information about the energy radiated away is somehow preserved on the event horizon of the merged black hole, a concept that has puzzled physicists for decades. Of course, there are still many questions to answer. For example, how exactly does the energy emitted during a merger relate to the entropy of the black hole? Is this a universal principle that applies to all black hole mergers, or are there exceptions? And what does this mean for the broader field of quantum gravity, which seeks to unify general relativity with quantum mechanics? These questions highlight the significance of the discovery, as they point to a deeper connection between the macroscopic behavior of black holes and the microscopic laws of thermodynamics. In summary, the discovery that black hole mergers follow thermodynamic principles is a landmark moment in astrophysics. It bridges two seemingly distinct areas of study, black holes and thermodynamics, and suggests that the universe operates under a set of interconnected laws. By observing the energy loss during mergers and linking it to the entropy of the resulting black hole, scientists have opened a new window into the fundamental nature of spacetime and gravity. This work not only deepens our understanding of black holes but also reminds us that the universe is a complex, interconnected system where even the most extreme phenomena are governed by the same principles that shape our everyday world. In the vast expanse of the cosmos, where the fabric of spacetime is stretched and warped by the gravity of monstrous black holes, a profound mystery has been unfolding. For decades, physicists have studied black holes as isolated entities, objects so dense that not even light can escape their grasp. Yet, in recent years, a startling revelation has emerged: these cosmic behemoths may not be as solitary as once believed. A team of researchers has uncovered an unexpected connection between black hole mergers and the fundamental laws of thermodynamics, a link that challenges our understanding of both gravity and energy. But how did scientists arrive at this discovery? Let's trace the path through the tools, techniques, and collaborative efforts that brought this revelation to light. The journey begins with the most sensitive instruments ever built, gravitational wave detectors. These machines, like the Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart, the Virgo Interferometer, are designed to detect the faint ripples in spacetime caused by cataclysmic events such as black hole mergers. When two black holes spiral toward each other, their collision releases an immense amount of energy in the form of gravitational waves, distortions in the fabric of spacetime that propagate outward at the speed of light. These waves, though incredibly subtle, can be detected by these detectors, which use laser beams to measure minute changes in distance as the waves pass through the Earth. The first direct observation of a black hole merger in 2015 marked a turning point in astrophysics, opening a new window into the universe. But it was only the beginning of a deeper exploration. The data collected by these detectors is not just a record of cosmic events, it is a treasure trove of information about the properties of black holes, their masses, spins, and the environments in which they reside. However, interpreting this data requires sophisticated computational models and algorithms. Scientists have spent years refining these tools to extract meaningful insights from the raw signals. For instance, the gravitational waveforms produced by black hole mergers are complex, with unique signatures that depend on the masses and spins of the colliding objects. By comparing observed waveforms to theoretical predictions, researchers can infer the characteristics of the black holes involved. This process, known as parameter estimation, has become a cornerstone of gravitational wave astronomy. But the connection to thermodynamics emerged not from a single event, but from a pattern across numerous observations. The key to the discovery lay in the energy released during these mergers. When two black holes collide, they form a single, more massive black hole, and the energy lost in the process is radiated away as gravitational waves. This energy loss is not just a byproduct, it is a fundamental aspect of the merger's dynamics. However, the researchers noticed something peculiar: the amount of energy emitted during these events seemed to align with principles of thermodynamics, specifically the concept of entropy. Entropy, a measure of disorder in a system, is a central idea in thermodynamics. In the context of black holes, entropy has long been associated with the event horizon, the boundary beyond which nothing can escape. The Bekenstein-Hawking formula, which relates the entropy of a black hole to its surface area, has been a cornerstone of theoretical physics for decades. But the new findings suggest that this concept might extend beyond the black hole itself, influencing the processes that govern their mergers. To explore this connection, the research team turned to a combination of observational data and theoretical modeling. They analyzed the energy outputs of hundreds of black hole mergers detected by LIGO and Virgo, looking for correlations between the energy released and thermodynamic quantities. The challenge was immense. Gravitational wave signals are incredibly faint, and distinguishing meaningful patterns from noise requires advanced statistical methods. The team employed machine learning algorithms to process vast datasets, identifying subtle trends that might have gone unnoticed with traditional techniques. These algorithms helped to filter out random fluctuations and highlight recurring patterns, providing a clearer picture of the underlying physics. One of the most surprising aspects of the discovery was the realization that the energy emitted during black hole mergers could be likened to heat dissipation in thermodynamic systems. In classical thermodynamics, heat is a form of energy transfer that occurs due to temperature differences. Similarly, the energy radiated during a merger might be seen as a form of heat being released into the universe. However, this analogy is not literal, it is a conceptual bridge between two seemingly disparate fields. The researchers proposed that the process of merging black holes might involve a form of entropy production, where the system transitions from a more ordered state to a more disordered one. This idea, while abstract, has profound implications for our understanding of how energy is conserved and transformed in extreme gravitational environments. The collaboration between observational astronomers and theoretical physicists was crucial to this breakthrough. Theoretical models provided the framework to interpret the data, while observational data validated these models and revealed new insights. For example, the team used simulations to predict how different configurations of black holes would affect the energy output of a merger. These simulations were then compared to real-world observations, allowing the researchers to refine their understanding of the underlying physics. The interplay between theory and observation is a hallmark of scientific progress, and in this case, it led to a discovery that bridges two fundamental areas of physics. Another critical factor in the discovery was the development of advanced computational tools. The sheer volume of data generated by gravitational wave detectors requires powerful computing resources to process and analyze. The research team leveraged high-performance computing clusters and cloud-based platforms to handle the computational load. These tools enabled the team to run complex simulations and perform large-scale statistical analyses, which were essential for uncovering the thermodynamic connection. The ability to process and interpret such vast datasets has revolutionized the field of gravitational wave astronomy, making it possible to explore questions that were once considered intractable. The timeline of this discovery is as much a story of perseverance as it is of scientific ingenuity. The initial detection of gravitational waves in 2015 was a monumental achievement, but it took years of refinement and collaboration to build the foundation for this new insight. The research team spent several years analyzing data from multiple mergers, gradually piecing together the patterns that hinted at a thermodynamic connection. This process involved not only technical expertise but also a willingness to challenge existing paradigms. The discovery was not a sudden epiphany but the result of incremental progress, driven by curiosity and the relentless pursuit of knowledge. The implications of this finding are still being explored, but they already suggest a deeper interconnectedness in the universe. If black hole mergers are governed by thermodynamic principles, it could mean that the laws of thermodynamics are not confined to the macroscopic world but may also apply to the extreme conditions of spacetime. This idea challenges the traditional boundaries between different areas of physics and opens new avenues for research. For example, it raises questions about how energy is conserved in the universe and whether similar principles might apply to other cosmic phenomena, such as neutron star mergers or the early universe. As the research continues, scientists are working to refine their models and test the thermodynamic connection with even greater precision. New observatories, such as the upcoming LISA Laser Interferometer Space Antenna, will provide additional data to support or challenge the findings. These missions represent the next frontier in gravitational wave astronomy, promising to reveal even more about the universe's most enigmatic objects. The journey to uncover the link between black hole mergers and thermodynamics is far from over, but it has already reshaped our understanding of the cosmos. It is a testament to the power of scientific inquiry and the enduring quest to unlock the secrets of the universe. Physicists find unexpected connection between black hole mergers and thermodynamics. This part of our deep dive into physicists find unexpected connection between black hole mergers and thermodynamics focuses on go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Physicists find unexpected connection between black hole mergers and thermodynamics. This part of our deep dive into physicists find unexpected connection between black hole mergers and thermodynamics focuses on give historical context, how our understanding of this general topic evolved over past decades, earlier missions, or discoveries that led up to this moment. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The discovery of a potential link between black hole mergers and thermodynamics has sent ripples through the physics community, sparking both excitement and skepticism. At first glance, black holes, those enigmatic cosmic entities with gravity so intense that not even light can escape, and thermodynamics, the branch of physics dealing with heat, energy, and entropy, seem like vastly different realms. Yet, the recent findings suggest that these two concepts might be more intertwined than previously imagined. But what exactly does this connection mean? And why does it matter? Let's dive into the questions that remain unanswered, the debates that are heating up, and the mysteries that continue to defy explanation. Thermodynamics is built on four fundamental laws, the most famous of which is the second law, which states that entropy, a measure of disorder, tends to increase over time in an isolated system. This law has shaped our understanding of everything from the behavior of gases to the eventual fate of the universe. Black holes, however, have long posed a unique challenge to thermodynamics. In the 1970s, physicist Stephen Hawking proposed that black holes aren't entirely black, they emit radiation, a process now known as Hawking radiation. This groundbreaking idea suggested that black holes have a temperature and, by extension, an entropy, linking them to thermodynamic principles. But until recently, the connection between black hole mergers, events where two black holes collide and merge, releasing immense energy in the form of gravitational waves, and thermodynamics remained largely speculative. The recent study that sparked this debate appears to have uncovered patterns in the energy released during black hole mergers that align with thermodynamic behavior. For instance, the energy output of these mergers seems to follow statistical distributions reminiscent of systems in thermal equilibrium. This is intriguing because black hole mergers are extreme events, governed by the laws of general relativity and quantum mechanics, yet they now appear to exhibit characteristics typically associated with thermodynamic systems. However, the exact nature of this connection is far from clear. Are these patterns a coincidence, or do they hint at a deeper, fundamental principle that unifies these disparate areas of physics? One of the most pressing questions is whether this link is a new law of physics or an emergent property of spacetime itself. Some physicists argue that the observed correlations could be explained by existing theories, such as the holographic principle, which posits that the information contained within a volume of space can be represented as a lower dimensional boundary. If spacetime itself has thermodynamic properties, then black hole mergers might be a way for these properties to manifest. Others, however, caution that the data is still preliminary. The study's conclusions are based on statistical analysis of gravitational wave signals, which are inherently noisy and complex. Without a direct, measurable link between the energy released during mergers and specific thermodynamic quantities, the connection remains speculative. Another layer of complexity arises from the fact that black holes are quantum objects, and their behavior is governed by the principles of quantum mechanics. Thermodynamics, on the other hand, is a classical theory that describes macroscopic systems. The challenge lies in reconciling these two frameworks. If black hole mergers exhibit thermodynamic behavior, does that mean that spacetime itself has quantum properties, or is there a deeper, unified theory that bridges the gap between quantum mechanics and thermodynamics? This question is at the heart of modern physics, and the recent findings may be a step toward answering it. However, the scientific community remains divided. Some researchers see this as a promising avenue for exploring the quantum nature of spacetime, while others argue that the evidence is not yet strong enough to support such bold claims. The implications of this connection extend beyond black holes themselves. If thermodynamic principles can be applied to spacetime, it could revolutionize our understanding of the universe's fundamental laws. For example, the second law of thermodynamics suggests that entropy increases over time, which has profound implications for the arrow of time. If black holes are part of this thermodynamic framework, their mergers might be a way for entropy to increase in a cosmic context. This raises questions about the role of black holes in the universe's evolution and whether they are simply byproducts of entropy or active participants in its growth. Yet, these ideas are still in their infancy. The study's authors acknowledge that more research is needed to determine whether these patterns are statistically significant or merely coincidental. One of the most intriguing aspects of this debate is the potential for new experimental tests. Gravitational wave observatories like LIGO and Virgo have already provided a wealth of data on black hole mergers, but the recent findings suggest that there may be more to uncover. If the connection between black hole mergers and thermodynamics is real, it could open the door to new ways of analyzing gravitational wave signals. For instance, researchers might look for correlations between the energy released during mergers and the thermodynamic properties of the surrounding spacetime. However, such experiments are not without challenges. the signals from black hole mergers are incredibly complex, and isolating thermodynamic effects from other variables would require sophisticated statistical methods and a deep understanding of both general relativity and thermodynamics. The scientific community is also grappling with the philosophical implications of this connection. If spacetime itself has thermodynamic properties, it challenges our traditional view of the universe as a collection of separate, interacting systems. Instead, it suggests that the universe might be a single, interconnected thermodynamic system, where the behavior of black holes is just one aspect of a larger, more complex picture. This idea is not without precedent. The holographic principle, for example, already hints at a deep connection between spacetime and information. But the recent findings push this idea further, suggesting that thermodynamics might be a fundamental aspect of the universe's structure. Yet, these ideas are still speculative, and many physicists remain cautious about drawing conclusions from the current data. Another open question is whether this connection is unique to black holes or if similar thermodynamic behaviors exist in other astrophysical phenomena. For instance, neutron stars, which are incredibly dense remnants of massive stars, also exhibit complex interactions between gravity and quantum mechanics. Could they also exhibit thermodynamic properties, or is the connection between black hole mergers and thermodynamics a special case? This question is particularly relevant because it could help determine whether the observed patterns are a universal feature of spacetime or an anomaly specific to black holes. If the connection is universal, it could point to a deeper, more fundamental principle that governs the behavior of all matter and energy in the universe. Despite the excitement surrounding this discovery, there are still significant hurdles to overcome. One of the biggest challenges is the lack of a unified theoretical framework that can explain both thermodynamics and the behavior of black holes. While quantum field theory and general relativity are the cornerstones of modern physics, they are incompatible at the most extreme scales, such as those near the event horizon of a black hole. The recent findings may provide a clue for reconciling these theories, but they are far from a complete solution. Many physicists argue that more experimental data and theoretical work are needed before we can say with certainty that a connection exists between black hole mergers and thermodynamics. In the end, the discovery of this potential link is a reminder of how much we still have to learn about the universe. It highlights the interconnectedness of seemingly unrelated fields and the possibility that the fundamental laws of physics might be more unified than we currently understand. However, it also underscores the importance of scientific skepticism and the need for rigorous testing before drawing conclusions. As researchers continue to analyze gravitational wave data and refine their theoretical models, the mysteries surrounding black hole mergers and thermodynamics will undoubtedly remain a topic of intense debate. For now, the connection between these two phenomena is a tantalizing glimpse into the unknown, a puzzle that challenges us to rethink the very fabric of reality. Physicists find unexpected connection between black hole mergers and thermodynamics. This part of our deep dive into physicists find unexpected connection between black hole mergers and thermodynamics focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Physicists find unexpected connection between black hole mergers and thermodynamics. This part of our deep dive into physicists find unexpected connection between black hole mergers and thermodynamics focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.